Hi, in this video we will discuss about the tensor analysis. Mainly tensor are a logical generalization of an vector. It is well known that we use the vector in so many applications, like vector has both magnitude and direction, and in tensor we will have certain other property, like we can represent certain physical property of an system. Suppose like in electrodynamics where we use, and mainly in also we use in the non-relativistic physics, that is in a Ohm's law, like J is equal to sigma into E, where here sigma is electric current and E is, sorry, J is electric current and sigma is electric conductivity. J is electric current and sigma is electric conductivity, and E is applied electric field. This is in case of non-relativistic case. Also we use tensor in general theory of relativity. Like first, let's expand this in terms of x component, y component, and the z component. Jx can be written as sigma xx ex plus sigma xy ey plus sigma xz ez, and similarly in y also sigma y x ex plus sigma yy ey plus sigma yz ez. Similarly jz as sigma zx ex plus sigma zy ey plus sigma zz ez. So these are the Cartesian component. In general we write as sigma ij component, like taking as in representation of a matrix, where here sigma I is not equal to sigma j. We take this will be principal axis. These terms are the, but these are the non-principal axis, where sigma ij is not I is not equal to j, and this is the principal axis expression. I can take value from 1 2 3 up to n. Like for example, stress of an elastic solid at a point depend upon the two direction. That is, suppose consider one material. When we apply the stress on here, stress on this material, it depend upon the area. What is the area of this solid and the direction of the force. First is area of the solid and direction of force. And electric conductivity of the medium is associated with the two direction. When conductivity in this rod, if you take, it also has the two component, that is direction of electric field, in which direction electric field is there, and also direction of flow of current, in which direction the current will flow. Suppose when you connect battery to some resistor or inductor, anything you can take. So if it current is moving in this direction, the flow of charge will be in the opposite direction, that what we take as conventional current. Let's see the Einstein summation convention. We use Einstein summation convention. Here in this video we will be just learning the important concept related to Kset. I will be not discussing in detail of this term. Like I will give in some tips and idea of how to solve the sum of the tensor. Repeated indices are summed over here. In case here, what we do here is summed over. Let's consider n-dimensional space and n-dimensional space and x power x2 up to xn are the set of coordinates in this space. Okay, it is important to note that x power n, these are the not the power. Okay, you should keep in this mind. So how we can write is aix in general form as a1 x power 1, a2 x power 2 plus so on up to an x power 1. This is the summing of the repeated indices. If the indices are repeated, so what we do is we just sum them. Suppose we have the differential form, like if f is equal to f of some x power n, x power 2, x power 3, so on up to x power n, then how we can write is here is df dou f by dou x1 dx1 plus dou f by dou x2 dx square dx2 d power x, so on up to dou f by dou xn d of xn. So in general, how we can write df is equal to dou f divided by dou xi into dxi. This is for a particular index. For a particular index, we will write this expression. Let's see some more example. Give me a second. Let's see some more example. Dou vi by dou xi. This can be written as dou v1 plus dou x1 dou v2 by dou x2 plus dou v3 by dou x3. Suppose if there is a double derivative, dou square phi by dou xi dou xi. So how we can write this term as dou square phi by dou x1 square, because if I take into indices as 1, so I can just dou x square plus dou square phi by dou x2 square plus dou square phi by dou x3 square. Okay, just a minute. Here let's see now about the contravariant tensor. Contravariant tensor, what is it and how we can write this contravariant, and there is one more term as covariant tensor. Now let's see the contravariant tensor. If component of a tensor A, suppose consider component of a matrix, these components, like how it has the components like A11, A12, A13, A21, A22, A23, A31, A32, A33. Like these are the components, or you can call it as a cofactor of a matrix, right? If a component of a tensor A transform between, like if it is getting transformed between x comma y comma z to x bar, y bar and z bar, like how this follows the rule as like a a bar j is equal to dou x bar j by dou xi into ai. This is the form that contravariant tensor that can be written. Then it contravariant tensor has the rank 1. In general, how we can write this contravariant tensor as, like we just expand this a bar, like I am taking mu1, mu2, so on up to mu p. Ls said I have written. Now how we can write dou x bar u1 by dou x, here I am taking I as alpha 1 into dou x bar u2 divided by dou x alpha 2 into dou x bar u3 dou x alpha 3, so on up to dou x bar up divided by dou x alpha p. This term has been finished now, right? Now how we can write ai? Similarly, I can written as a of alpha 1 alpha 2 so on up to alpha p, because here this term as this one, because you can see here, let's change color. You can see here, this is I, a bar j, this has j component, dou x bar, this is also j component, and dou x I, you have to note this is I, and a I, you have to note down the indices. What are the indices they have? According to that, you have to expand. Example for this contravariant tensor are like tangential vector. One more is, yeah, this is enough. Now let's see the covariant tensor. If component of a tensor are transferred between, if the transformation of a component, like what I have done in the like matrix, taking matrix a11 up to a2 a33, right? So if these components of this matrix are getting transferred between x y z to x bar y bar z bar, and like how it get is transferred from here to here is aj is equal to dou xi by dou x bar j ai. Like you have to note down here j component, I component, j component, I component. In general, how we can write, in previously I have written, previously it has a bar j is equal to dou x by bar j dou xi into ai. This is the component. Like now it has gone to lowercase. Now how we can write this in general form? J is termed as, I have written mu1, mu2, mu3. Similarly, now j is written as mu1, mu2, so on up to mu p. Now this dou x I can be written as alpha I. Alpha I can be, I will take as alpha 1. Dou x bar j can be mu1 into dou x alpha 2, dou x bar mu2, dou x alpha 3. I think you are getting now. Dou x bar mu3, so on up to dou x alpha p, dou x bar mu p. Right. Next, this term, how we will write this term? A, here alpha 1, alpha 2, so on up to alpha p. This is the general representation of a covariant tensor. What is, like, what is the example for this? A normal example is a normal vector to a surface is covariant tensor of rank 1. Means suppose not consider a surface like this. So this is the normal vector, and this normal vector is a covariant tensor which has a rank of 1. Suppose, let's see some example, because if you go on with here, it will take time. I will go for example now. A covariant tensor has component 2x minus z, x square y and yz in Cartesian coordinate system. Find its component in cylindrical system. Like what they have given here, component. Let's write the component what they have given. I will write as ax is as x component and ay component, az component every time. Now what they are asking is find the component, cylindrical component. So what are the component? You have cylindrical, x is equal to r cos phi, y is equal to r sin phi, z is equal to z. Now just put in this equation. Like I am getting 2 x is equal to r cos phi minus z of the same r square cos square phi r sin phi sin y terms as r sin phi into z. Right. In instinct convention, like we can write like what you have seen in previous. A bar of x can be written dou x bar 1 ax plus dou x square by dou x bar plus dou x cube by dou x bar az here ay. Now what you are going to do is just for convention x bar can be written as x and x square written as xy, x cube is equal to z. Now write ax bar is equal to dou x dou r ax plus dou y dou r ay plus dou z dou r az. Differentiation of x y z is there. Now we have to differentiate with respect to r. Now cos phi ax term as this 2r cos phi minus z plus sin phi r cube cos square phi sin phi plus 0 because z component has 0 term. Differentiation of z, there is no r term, so that is 0 term. So next we are going to get 2r cos square phi minus z cos phi, just multiplying it, plus sin phi square cos square phi into r cube. Right. Similarly you can do for az, ay, a bar z. Similarly you can write, like I will be writing what is the final answer for ay bar. Like you will be getting like, okay, I will write r power 4 cos cube phi sin phi minus 2r square cos phi sin phi plus 2r sin phi. For az bar you will getting az bar is equal to, like, it is easy one, dou x bar 1 by dou x cube, sorry, r sin phi z. This is the value you will be getting. Now let's go for symmetric tensor. Like a tensor is said to be symmetric, like we have seen in the matrix also. Like how we can define in case of matrix, because a transpose to a, this will be symmetric matrix, right? Similarly in case of tensor, what we are going to do here, we will be having some of the components like m and n form. So if amn is equal to anm, then what we call this as an symmetric tensor. Okay, next is antisymmetric tensor. In case of antisymmetric tensor, just as an in the case of antisymmetric matrix, a dagger is a transpose is equal to minus of a. Here we have a m n is equal to minus of a n m. Some other types of tensors are there, like that no need to discuss. In the next class we will be discussing about Lewis-Witt tensor and chronicle delta tensor, and some other fundamental properties of a tensor we will be discussing. Like I will be mainly discussing on important concept, not in detail. Thank you.